Hi, it's a great honor to be able to present NGScope, a fine-grained telemetry tool for next-generation cellular networks. I'm Yasheng Xie, and this work is a joint work with my supervisor, Kyle Jamison. Nowadays, cellular network has attracted huge attention from the research community. In this work, we target at building a telemetry tool for the whole research community to conduct measurements inside commercial cellular networks. This figure shows you the typical structure of a cellular network. The base station provides wireless connection between the user equipment and the network. All the base stations are connected via a backhaul network, and the traffic from the cellular base station are routed to the mobile core network and then to the cloud. We can perform telemetry inside this network from many aspects. First of all, we can conduct end-to-end telemetry by sending data between two ends of the network. By doing so, we can measure the packet status like the packet arrival time, packet RTT, and packet loss to infer the network status. But this method treats the network as a black box, so naturally it lacks the insight into the cellular component. On the other hand, we can perform telemetry inside the network. We can deploy some software, hardware inside on the cellular base station, inside the backhaul network, or in the core network. But it requires the cooperation from the service providers, which is very hard for most of the researchers. We can also perform telemetry at the mobile device. Each device only provides limited view of the network. If we want to scale the measurement, it involves deploying the measurement software on a lot of mobile phones. That is very that costs a lot of implementation costs and raise a lot of privacy issues. So what's the options left? We observed that we can perform telemetry at wireless link because wireless is a broadcast medium, so that we don't require any cooperation from the service providers. Also, by listening to the base stations, we don't need to care about how many users is talking to the base station, so that we decouple ourselves from the density of the user equipment. This method is promising, but what kind of data we can get from this kind of telemetry? To answer that, let's look at the physical layer structure as a background. Actually, both 4G and 5G use OFDMA in the physical layer, which divides the time into subframes and the bandwidth into a lot of small blocks called physical resource blocks. To transmit data on OFDMA, cellular network use a centralized traffic scheduling, which means the base station or the cellular network controls every aspect of the transmission. Specifically, the base station controls how many PRB is allocated for each user inside each subframe. It also schedules how many bits inside each PRB. And the base station change its configuration across subframes. The base station also schedules the retransmissions because wireless is typically suffers from retransmission errors. The base station group all the bits in one subframe as one transfer block. So if any bits inside the transfer block is received with error, the base station will schedule a retransmission of the transfer block in the later subframes. The base station also schedules the traffic for all the users, and it multiplexes the user traffic across time and frequency, as this example shows. The base station also schedules both downlink and uplink. And the network also configures, schedules different number of base stations to transmit data to the user. More base stations is allowed to transmit simultaneously to one user. So to summarize, the cellular network controls every aspect of the transmission between the base station and the user. But how does the base station tell the user about the scheduling result? Actually, cellular network has a dedicated design for this. So inside each subframe, the cellular network has divided into the control channel and the data channel. The data channel is used to deliver user data, and the control channel is used to deliver control messages. And inside the control message, we have all the scheduling results. So the UE has to decode the control channel before it can decode the data channel. And a very important observation we have is that the control channel is not encrypted. Of course, the data channel is encrypted so that no one knows what the user or the base station is transmitting. But we don't need to decode the data. We can get the number of bits transmitted in each subframe and the number of bits transmitted by each user and how many users, all this detailed information by purely looking at the control messages. Therefore, if we can decode all the control message, we are able to monitor the cellular traffic at millisecond level granularity. What we can do with this kind of detailed, fine-grained measurement data? Here, I just list some example, and I hope our tool can enable more applications. So the first example is that we can analyze the user traffic. Here, I plot the allocated PRB for a mobile device when the mobile device is watching YouTube. You can see obvious patterns. And this pattern actually matches with how YouTube works. With the network usage of each user, we actually can know how busy the base station is. So in this figure, I plot the PRB usage of the base station. You can see that the base station is very dynamic. And if we know how busy the base station is, we can actually estimate what's the potential capacity for the mobile devices. Because the capacity of the mobile device equals to the available bandwidth multiplied the bit rate. And the available bandwidth consists of the allocated bandwidth and the idle bandwidth. For example, if the user is able to use all the idle bandwidth, then the capacity is very high. But if the user is not the only user of the base station, then the idle bandwidth is much smaller. So we need to know how busy the base station is. And if we have accurate capacity estimation, then we can improve the performance of a lot of applications running on top of cellular network, like the congestion control, video streaming, and video conferencing. They all require accurate capacity. But all these aforementioned applications rely on one assumption. That is, we can decode all the control messages. But can we do that? Actually, it's quite challenging because typically each user only decodes its own message. But now we are talking about a tool that can decode all the control messages inside the control channel. So to explain why this is challenging, let me explain how the control messages are transmitted inside the control channel. Actually, the control channel contains a lot of bits. So the cellular network group every 72 bits into one control channel element, one CCE. The base station can transmit one message inside one CCE or one message inside multiple CCEs, like 4 or at most 8 CCE. So the number of CCE is called the aggregation level. When the user decodes the message, it needs to do 3 jobs. First of all, locate the message. So which CCE contains the message? And the second job is to verify the correctness of the message after decoding. And at last, it needs to identify the receiver. If the receiver is itself, then okay, you got your message. And the user heavily rely on a temporary ID of itself to do the 3 tasks. The temporary ID is the Cell Radio Network Temporary Identifier. We call it C-RNTI, which is a 16-bit sequence. And this C-RNTI is assigned by the base station when the user builds a connection with the base station. So the user rely on C-RNTI to reduce the search space. we have so many CCEs that may contain the message, but the user will perform the hash function on the C-RNTI to find its own search space, which is smaller than the total number of CCEs we have. And the details about the hash function can be found from the standard. And UE also rely on C-RNTI to simultaneously perform user identification and message verification. Let me explain this in a little bit detail. So in the encoding process, the base station encodes the control message and then calculates the CRC and then XOR the CRC with the C-RNTI of a user. And the XOR, the value will be appended at the end of the control message as the appended CRC. So at the receiver side, the user will get the appended CRC and then XOR with its own C-RNTI to get the derived CRC. And then it will compare the derived CRC with the calculated CRC from the control message. If these two CRC matches, it proves two things. First of all, the decoding is successful. Second, the received this message is indeed for this user, because another user with a different C-RNTI will get a totally different derived CRC. But in our work, we don't know any of the C-RNTIs. So how can we decode the control message without knowing the C-RNTI of any user? So the first step is we still need to reducing the search space. We don't use C-RNTI to do that, but we rely on one observation. That is, not all the CCE contains control message. Some of them are empty. So empty CCE contains no energy. Then we can look at the energy and find the empty CCE. Then we group the search space into trees, because two CCE can be grouped together as one to transmit one message. So we first identify the empty CCE in the tree and then further prune the tree. Then we can significantly reduce the search space. And we also need to derive the C-RNTI of the users, right? Actually, we derive the C-RNTI like this. So when the user performs the decoding, it will use the appended CRC XOR with the C-RNTI of the user to get the derived CRC. But if the decoding is successful, then the calculated CRC equals to the derived CRC. Therefore, we propose to XOR the calculated CRC with the appended CRC. Then we can get the C-RNTI. Because the XOR operation is linear, so it can be reversed. But this method only works if the decoding process is successful. But we don't know the decoding is successful or not without knowing the C-RNTIs. Therefore, to solve this problem, we propose 4 methods: the child ancestor matching, search space matching, checking the regular encoding errors, and temporary UE checking. You can refer to our paper for the details about these 4 methods. So at last, I want to introduce some interesting findings we obtained using NGScope. First of all, we want to understand the transport block errors in mobile networks. So in this measurement, we connect the mobile phone to AWS cloud and let the AWS cloud to send data to the mobile users. And we then move the user to different locations with different signal strengths. We also test with different transmission speed from the AWS cloud. And this figure shows us the result. For this result, the x-axis is the overload and the y-axis is the signal strength. The color means the error rate. The red color means higher transport block error rate. We can observe from this figure that at each location, if we have higher overload, or higher transmission speed, we have higher transmission error rate. But across different locations, even though they have different signal strengths, they don't have we don't observe obvious patterns in the transmission errors. This is very interesting, and our hypothesis is that when the base station is transmitting with higher speed to the user, then inside each subframe, the base station needs to transmit more bits, which results in larger transfer block. And a larger transfer block with more bits has higher chances to receive bit errors. So to verify that, we also plot the transfer block size versus the transfer block error rate. We can see from this figure clearly that the error rate increases with the transfer block size. We also want to demonstrate that NG-scope is able to track the network capacity accurately. So we plot the estimated capacity in these two figures. Different color means different the capacity from different base stations. You can see from these two figures that the capacity for the Samsung phone varies a lot, but for Xiaomi phone, there's one base station that provides stable capacity. To understand why, we dig deeper using NG-scope, and we found that there's a special base station there that only has downlink. So it doesn't serve any user in normal cases, and it only works when the user has carrier aggregation enabled and want to download a lot of traffic from the network. In the end, we want to further prove the effectiveness and accurateness of the derived capacity using NG-scope. We actually build congestion control algorithm using that information. We write a whole paper to describe our congestion control. Please refer to our CCOM paper for more details. In the end, I want to advertise a little bit about NG-scope. Our NG-scope is now open source. Please check our GitHub for the source code, and we are still under active development. We are adding more functions and decoding more messages.